So our next plenary lecture is by Professor Carl Åström from Lund in Sweden. Carl Åström is one of the founding fathers of control theory. His name is very well known. It is very well known in Russia. When I was a young graduate student, I knew his book, and I first knew the name from your book on stochastic control, and it was 10 years before I heard live your first lecture, which was in '84 at MTNS in Stockholm, which was organized by Professor Lindqvist. So I think everyone knows Professor Åström, and today he will speak on relay. Where's the type? Relay autotuners. Yes, welcome, please.
Well, thank you very much for this introduction. I would also like to thank the organizing committee very much for inviting me to do this. I was a bit hesitant when I got the letter from Fradko, because I've not really been working much in nonlinear systems. So I looked to the scope of the conference, and I noticed a couple of words there. You spoke about theory and applications, nonlinear system and identification. And I was thinking, can I really say something meaningful related to this? And then I decided to do it. And the main reason was personal, because there is hidden here a fundamental theoretical problem that I've not been able to solve, and several of the other smart people I've been working have not been able to solve it either. So I'm thinking now, it's a nonlinear problem. So my main motivation for this was very selfish. I hope that somebody will come up with an idea to solve this problem. This will deal with relay autotuners for PID control. And I like short titles, so I just skipped the PID control in here. And these were relay feedback, which is, in a certain sense, the simplest nonlinear feedback system you can have. And as you will see in the end, it's not that simple. The application I will talk about has widespread industrial use, not as much as the Kalman filter, which is 100 million. In here, we're at least talking about millions of feedback loops that are using this idea. I will do some analysis, and then I will present an unknown problem that I would like to have help for solving. I would also like to pay homage to Yakubovich. I met him about a handful of times at internal Russian conferences. And for me as a young researcher, he was extremely kind and helpful to me, and we also communicated by letter, so I'm very grateful to him. I also have a colleague, Tore Hägglund, which I've been working with for a long time with this. And then I have a new PhD student and a young faculty that I'm currently working on these problems. So, what about PID control? It's the most common controller. Here is a quote from 2000, where you look at typical industry, 98% of the controllers use PID feedback. You can go back 10 years. Here's an engineer looked at Canadian pulp and paper, and he said 97% use PI control. I haven't seen any more recent. He also has looked at them quite well. About half of them worked very well. 25 are dysfunctional. They are increasing fluctuations instead of decreasing fluctuations. And 25 are dysfunctional. And the main reason is bad system design, problems with hardware, but bad tuning accounts for 30%. So that's a good motivation to try to do automatic tuning to get rid of these problems. So that is something that I've actually been concerned with for quite a while. So here then is the plan. After the introduction, I will talk about the basic relay autotuner. Then I will talk about current work to make them much better. And then I will introduce what I call the million-dollar question, to classify all systems where this will work for. And that's a very clean mathematical problem that I don't know the answer to. So here's the idea of the relay tuner. You have a feedback loop, and to tune it, you flip over a switch in here, so the process runs under relay feedback. And that's like a thermostat. And here I show some signal traces. Here's the relay, which switches, and here is the output signal. And if you look to see, you see roughly what's happening here is that the input and the output are 180 degrees out of phase. So an experiment like this gives you immediately the frequency where the process has a phase lag of 180 degrees. And also, if you look to the amplitudes here, you can get an approximation of the gain of this. So together with Tore Hägglund, we made patents of this in the early 80s. And we wrote the paper in Automatica in 1984. And it turns out that these devices have some nice features. You know, the relay oscillation gives the gain of the frequency, and then you can just move this point here to some other area with PI control. You have 2 degrees of freedom. With PID, you can change the tilt of it. So we rigged up a simple version to tune PID controllers based on this, and it has some very attractive features. For example, it's very short tuning time. Here I've done an extreme example. It's essentially a heat conduction process. You see here the step response. Starts very slowly, and then it finally goes up, and it takes about 100 units to be reasonably close to steady state. If you do a relay experiment, you see already in 0.4 time units, you have got enough information to tune a PID controller. So it's much better than to do step responses if you are doing this. There are a few practical details I will mention very quickly. You have to bring the process to equilibrium, measure noise levels, you introduce hysteresis in the relay, you initiate the relay oscillation, you monitor half periods, and you check for steady state, compute controller parameters, resume PID control. With hysteresis, if you are using describing functions, you are approximately picking up this point of the transfer function. So this simple idea has been very useful. And when preparing this talk, I picked up the first industrial test, which was done in 1982. We took an Apple II computer, which we were using in the lab. We tied it up to the industrial process control system at the Sugar Works in Malmö, and here you see the experiment. Here is the control signal, the relay, and here is the output. The signals are not very clear, and here then it's gone into automatic, and we switch it up like this. So it's an example where it's working pretty well. Here's another example. You can also use this to figure out if you don't know the gain of the process, which is quite common. So here's an example of this, that here's a tuning period, and then we test it by making a step change. It does pretty well, and in this case, the auto-tuner discovered that the process has negative gain, so the operators don't have to be concerned with that. This has been implemented in many, many different ways. Before I do this, I'll show you an interesting experiment. We were up at an industrial plant in northern Sweden, very close to, it was a small chemical preparation for pulp and paper industry. And they had about 100 loops. And then it will typically take about 2 to 3 weeks to commission such a system. Now with the auto-tuners, we did it in 5 days. You connect one loop, tune it, connect another loop, tune it, etc. And then the people came to us and said, we have this beastly process here that we've never been able to tune. Can you help us with that? So we took one of our little boxes and connected it to this. And here's a strip recording where time runs in this direction, because the unit we had no digital recording on it. So you see in here, this process is oscillating. They had a PID controller with a gain of 8, an integration time of 2000, no derivative action. Around shortly before lunch, we switched it into manual. And then you see, stop the oscillation when it starts to drift. At 2 o'clock in the afternoon, we push the tuning button. And then in here you see, here is essentially where we're determining the hysteresis level. And then you see you get something here that looks like an oscillation. And we were waiting and waiting. This is 2 o'clock in the afternoon. At 8 o'clock in the evening, it goes to automatic control. And look what it does. Beautiful control. And you see what it does. It reduces the gain, and it introduces derivative action into it. So I think this is a very nice example. And to try to tune manually something that is as slow as this, of course, will take a long time. So they have been manifested in many ways. It's called one-button tuner. You can just push a button here to tune it. We can also generate gain schedules automatically, because when you're using the simple controllers, processes are often nonlinear. So then we can, you pick up a scheduling variable, you set up a table, and then you operate in a certain region, you push the tuning button. So you build up gain schedules automatically. You can also introduce adaptational feedback and feed-forward gain. And there are many, many versions of this. There are single loop, and they're involved in DCS systems, etc. And I'll give you a couple of industrial examples. So when we started, we worked with local Swedish companies. And then in the end, they were, the patents were acquired by a large American company that's called Emerson. They put into one of their large DCS systems. And of course, ABB did the same. So in here, this is where the mass use is coming. And these are typical distributed control system, both of them. And then there are also single loop controllers in here. I'll give you experience from Emerson, and here's what they say. The tuners can be used by production technicians on shift with complete control of what's going on. So in other words, when they are running the plant, they can take the regular plant personnel and they can run it. The operator is aware of the tuning. And what's interesting, they can teach this and become useful in less than an hour. Many industrial people are asking for PhD-free control. That is, controllers that can be used by people who are not PhDs. And this is clearly one example of this. And this is documented in this paper that we are sitting there. So that was a little bit about the basic relay autotuner, which was done, 35 years ago. And then, of course, it took about 10, 15 years to make it mature. And now we'll talk a little bit about more advanced autotuners. Number one, there has been a dramatic increase in computing power. I still remember the first one we put in, the company said, we can use it if you can squeeze it into 2 kilobytes of code. And of course, nowadays we can do much more. So we can do better modeling. And one thing that we have discovered quite recently is that it's very useful to introduce an asymmetric relay. So it's a little step in one direction and a much larger step in the other direction. I will tell you later why this is so good. We can also do system identification. So instead of waiting for steady state like we did in the old one, we just get some transient and we run system identification to it. And also, if we don't get enough information, which I give you insight, we can add additional signals to it. We can also make assessment here of several models. So instead of doing the very simple thing we did first, we can now really start to figure out what complexity of the models do we really need in order to describe this. We have also learned a lot about design of PID controllers. And it's quite common right now to assess low disturbance attenuation by minimizing the integral of the absolute error when you put in a low disturbance at the process input. Robustness, we are using maximum sensitivities. Also, we have to keep control of noise injection, so we bound L2 norm of measurement noise. And then there are very efficient constrained optimization algorithms that you can run to do PID controllers that do this. We are also starting to look to multivariable systems. And I mentioned MPC here. One of the stumble blocks for using MPC is lack of models. And we think that this type of techniques can be used extremely favorably to obtain the models you need for model predictive control. So here's a little bit about design of PID controllers. Many processes in industries have monotone or almost monotone step responses. And you can often approximate transfer functions by a time delay and a time constant. And there's one parameter here that's important. I call it the relative time delay. It's the ratio of L divided by L plus T. So if T is equal to 1, the process is dominated by time delays. If tau is 0, it's dominated by dynamics. And then we have obtained large batches of representative transfer functions from our colleagues in industry. So we have about 150, 200 test examples that we are running to. And then on this test example, we've been designing PID and PI controllers. And we've been plotting the integral gain of the PI controller, which is a reasonable measure of performance. High gain means good performance. And we also plotted over the gain of the PI controller as a function of the normalized time delay. We got a curve like this. So here's the normalized time delay. And we see that if you are time delay dominated, I think I'm going to remove the flowers. You're interfering with the laser. PI and PID gives essentially the same result. And then as we get more and more dynamics, you see PID gives roughly twice up to 0.5. Down here, there's a very big difference between PI and PID controllers. And so here, down here is a region where improved modeling makes a lot of difference. So up here, we can just use a PI controller. In here, derivative action may pay off. We can still use a very simple model to do this. Down here, it pays a lot to do much better modeling. So by doing empirical studies of this, we learned something. And we also have to do initialization and to use the asymmetric relay. It very often happens that you have friction in values and things like this. So therefore, we always start with a little exponential increase in here. There's an absolute limit to how much we can change the control signal. But the important thing is how much do we allow the control signal to fluctuate. So there's a simple feedback loop that arranges this. So that is one thing for the... And also this startup feature here, it gives you actually quite good excitation. Here I show the difference between a symmetric relay and an asymmetric relay. So this is essentially the spectrum of the control signal. And the blue is the ordinary relay. You see you get the first period, and then you get the third harmonic sitting up here. They are quite spread apart. When you use an asymmetric relay, you see you are getting a peak here, and you are getting two peaks down here. So the asymmetric relay gives you much better excitation. Not just around this frequency, but it's spreading out a little bit. So it's a useful, practical little thing. And here are some typical experiments. And the only reason for showing this one is that this process here is time delay dominated, and this one is dynamics dominated. And then you see in here, the oscillation is practically metric, even if we have asymmetric relay levels. Down here in this area, the oscillations themselves are asymmetric. So by just measuring the ratio of this, you actually get a feel for what the value of the normalized time delay is. So that's a useful little thing. Now, I'm going to skip this. When you do system identification, it's very useful to try to fit the spectrum of models. You know, these are some very simple ones. Here are some slightly more complicated. And then we can start to use models of second-order dynamics with a zero and a time delay in here. So by doing system identification, and you go through the usual system identification exercise, you calculate you see the loss function runs down, and then you look at the Aki-Iki criterion. In this case, it tells you that you are much better off by using second-order models instead of using what is customary for PI and PID control. So system identification here can help us a lot. Here I show typically border plot that you get, and you see some interesting things. You get errors in steady state, but down here, where you have good excitation, you really get good estimates of the transfer function. The phase is better, but particularly in this area where the phase is around 90-100, we get pretty good models in here. And normally integral action will take care of this, so that's the reason why simple ones work well. But in this situation is that sometimes it's really worthwhile to get better low-frequency models. And that's something we can achieve by introducing chirp signals. So after making the relay experiment, which we keep short, we know roughly what something about the model, and then we can design a chirp signal that is designed to give better excitation in the other area. And here I show two curves. Here is the output of the relay experiment and the process model. And here is the output and the process model with a chirp signal. And with this chirp signal, you see, you also get a little bit of DC component on it. And now you can really squeeze down here what the transfer function looks like. So adding an extra experiment really gives you a lot of, it gives you much better models. And I've shown you here noise-free data, but you get essentially similar things when you have noisy data. So now if you just do the simple experiment, you get this. But if you're now adding the chirp to it, you can really get much better modeling to this. So that was a little bit about the empirical stuff. And now we come to the really fun stuff, the million-dollar question. We've been running this type of systems on a lot of simulation examples. We've been running them on a lot of industrial processes where we gather information. But we still don't know this. Take a linear time invariant system, connect the relay here, and then we have simple feedback loop. And we just do relay without hysteresis. And I'm very interested to know, give me a class of transfer functions where I get a unique limit cycle of this system. And if anybody could come up with a smart solution to that, I will be extremely happy. I've been trying myself for many years. I have had some very strong collaborators who've been trying to help me. And we have come a little way, and we have lots and lots of examples, and we have lots and lots of counterexamples. But we have not been able to come up with a nice class of transfer functions here where this is going to work. So this brings us, of course, to relay feedback. I used to say that these are the simplest nonlinear feedback systems, but I'm not so sure anymore. And these systems are very common, not only here. Delta sigma modulators are very common. Admission controls in network. It's a simple model for Coulomb friction, etc. And it's a classic field. And a lot of the very interesting work have been done here in the Soviet Union. And I listed here, some of the main research, Andronov, Witt and Tsypkin, Flugge-Lotz, who immigrated to Stanford. In Cian's book on engineering cybernetics, there is actually a full chapter on relay feedback. And of course, we have Tsypkin, who did stellar work on relay feedback. And you have many more. You had Filippov, who looked at differential equations with discontinuous right-hand side. His work is extremely useful when we are going to simulate. You have, maybe you should describe the problems by differential inclusions instead. You have Atkins sliding mode, you have hybrid system. So there's a lot of work sitting out there. And for example, to figure out the limit cycles, we can progress in many ways. We can find necessary condition, and we can find local stability, which we have done. Global stability for specific cases have also been done, and there are both frequency domain conditions. In a very simple way, if you plot the Nyquist curve in here, and then you do describing function analysis, with a relay you get this, so you have potential limit cycles in here. That would be a very, very simple way of doing this. So what I will do now is that I will go through a number of examples where you have strange behavior. But first I do a little bit of analysis. We have a linear system, and I do this without time delays. You can easily extend this to time delays if you want to. And we assume that you have a relay that switches when CB, we assume that CB is equal to 0, so there's no direct term in the controller. And then we start at the switching point, and then we integrate over a half a period. And then we find out that the condition for oscillation is that when you follow a half trajectory around, you will find that the time for a half trajectory, it's when the relay switches again. So this function here has to be epsilon over d, where epsilon is the resist width and d is the relay. So there's a function in here which tells us precisely values of h where we can have a limit cycle oscillation. This result is about 20 years old. So with this one, we can actually analyze specific cases. We calculate this function, and then to find when it's 0, and then we also evaluate the control signal over the period to make sure that it doesn't switch in between. And the periodic solution corresponds to the following initial conditions. So that's a pretty straightforward linear systems calculation, which also can be extended to systems with time delays. For stability, for local stability, we can calculate the Jacobian of the Poincaré map, which has a nice explicit solution. So once we got the age, v is essentially the velocity when it's switching. So you have a very nice expression for this. And you may notice that if we have a first-order system, W is going to be 0. So when we have first-order dynamics in here, it switches very quickly. There's a result of global stability by Goncalves and Lyapunov. And I think it was also inspired by Megretsky, who was coming here from St. Petersburg, that if you have a particular solution, you can also analyze the global stability of that particular solution by using Lyapunov functions and Jakubowicz LMIs. So for a specific system, we can really calculate what happens. So what we do then is that we take this function. We can easily calculate the gradient of this. You can do very efficient Newton-Raphson iterations. We compute the steady state, we check the y's, and then we check for global stability. So in a specific case, it's a very simple problem to analyze. There are also nice frequency domain conditions. If you look to what this condition means, It means that if you calculate the pulse transfer function of this system, you evaluate when z is equal to -1. This should equal epsilon over d. So this gives us a frequency domain interpretation, which is very natural. When it's oscillating, you apply sample data theory. Tsypkin did this. If you use the expression for the pulse transfer function in terms of the regular transfer function, you have this expression. And if you apply this, you get the Tsypkin locus, which is exact instead of having the describing function analysis for this. So here then are some examples that we've been through. If you have an integrator, you get chattering. If you have a double integrator, you have infinitely many limit cycles. If you have n first-order system, you have n-1 limit cycles, so one of them is stable. If you have systems of this type, you have one stable limit cycle. If you have first-order system and time delays, you have a very interesting situation. You have one stable limit cycles. And then you have, it's an infinite dimensional system, so that's an infinite memory. And then you can load it up with something that's a periodic solution. If you match this to the switching, you can get a stable limit cycle. You can actually get many stable limit cycles to this. But there's only one stable limit cycle. If you have an unstable system, you have one limit cycle if the time delay here is not too large. So there are a number of cases here that we understand quite well what they behave, and many of them correspond to things similar to industrial situations. Now let's look at the weird cases. Here's a simple system, unstable with oscillatory behavior. And here, even if you have a symmetric relay, you get asymmetric oscillations. So these are clearly cases that have to be excluded. Here's another one. If you plot the microscope, looking something like this. In this case, you have two stable limit cycles. And this system is fairly benign, it doesn't behave too badly at all. And now we are coming to the bad cases. And here I had the real pleasure to have Barabanov from St. Petersburg in Lund. And we were working with Karl-Erik Johansson, who was a PhD student at the time. He's now a stellar professor at KTH. Anders Ranzer is sitting in here, and Barabanov and myself. And we were trying to understand a system of this type. So here is a fairly nice system. You see, it has pole excess 1, so we have chattering. But you also have other dynamics. So in here, we have a very strange limit cycle. If it's a three-dimensional system, so we can plot it in three-dimensional space. So the limit cycle looks like this. It moves around here, and then it hits the switching plane. On the switching plane, you start to get chattering. So it's chattering out to this limit here, and then it moves up here, hits the switching plane, chatters around here, and then it comes back. Also, simulating this is not easy, because in order to do this well, you have to switch over and use Filippov solutions when you're solving this. So this is one case that we're going to have trouble with. And you can guess that you have chattering because you have pole excess 1. You can also get an insight because the inverse dynamics is unstable. And that's why you're moving out of the switching plane when you have it there. Here's another interesting example. It's now a system with pole excess 2. We still have unstable zeros. So with pole excess 2, if it was nothing else, we can have, if it was just 1 over s squared, you can have infinitely many limit cycles, which are just circling around. In here, you get a very interesting limit cycle, which I have an illustration on the next slide. So now this is a projection because it's a fourth-dimensional system. So here's the switching plane. So what's happening here? We have a limit cycle where it's shooting out of the switching plane, then it comes back. And then you see we have a line here. And what's happening is that the solution is circling down the line with decreasing amplitude. So it's coming in here and it's circling down the line with decreasing amplitude. And since the inverse dynamics is unstable, it comes pretty close to this point in here, and then the oscillations start to increase again, and then it shoots out. So we have a limit cycle here with some very interesting switching phenomena. So even if I said that relay feedback is the simplest nonlinear systems, I hope that these two examples will convince you that they are not that simple. So that was a little bit about what I call the million-dollar question. So let me now try to summarize about what I've done. I gave a little introduction and then I spoke about the basic relay autotuner. It's really a very simple idea. You switch in a relay, you get a limit cycle oscillation, you analyze this, and then you can go back and get a PID controller. And today, with increased computations, you can do this in a much better way. And we are actually working quite actively on that in the department right now. I brought up the million-dollar question, which I would be very happy if somebody comes up with some ideas about. You know, there are interesting things happening in nonlinear systems right now. For example, Anders Rantzen mentioned to me on the plane that there are interesting new results emerging on limit cycles in nonlinear systems, which may apply to this. So then we come to the summary of this. I think the beauty of the relay autotuner is that it gives automatic excitation in a good frequency range. If you're going to plan a system identification experiment, you need to know something about the process in order to excite it in the right way. Here with the relay, we're exciting it where the phase lag is about minus 180 degrees. So we're automatically injecting a lot of energy at this frequency without knowing this frequency a priori. We can have short experimentation time. There's no reason to wait for steady state. We can just use a transient and run system identification. And industrially, there's a big virtue in having a short experimentation time, because then not very much can happen into this. There's very good industrial experience of it. There are millions of loops, both in single loop controls and DCS systems, and there are many potential improvements. And so we have this challenging, unsolved theoretical problem, which I would very much like to see solved before I disappear from the scene. Thank you very much.
Questions, please. I have a question. Does it make sense to try to apply it to biological systems like heartbeat, to improve it using relays and switching?
Biological system is not my forte, so I would just say maybe. If I may be allowed to tell a story about Jakubowicz, related Jakubowicz. I was at the mathematics department at Brown University, which was run by Joe LaSalle. And he had just finished this little book about Lyapunov of stability. And there was a student coming up and asking him, Professor LaSalle, would you accept me as a PhD student working on stability problems? And Joe LaSalle said, well, I don't really think so. I think it's more or less a closed field. A year later, the Popov, Jakubowicz, Kalman theory came around, which totally changed the stability field. So I think it's very difficult to make predictions.
Thank you. Any more questions and comments? So thank you very much.